Hello and welcome to the first part of my talk in the online event Generating Analysis Past, Present and Future. In this part, we will introduce the variation of the volume and the minimal submanifolds as critical points and the notion of stability. So let's start. So the talk is divided in three parts. The first one, I introduce just the basic notation that we will use throughout the whole series of this talk. Then we will compute the volume variation, the first and the second one. And finally, we'll introduce the notion of stability and index of a minimal immersion. So through all the talk, we will study submanifolds of an ambient manifold. So I will denote with a overline everything that is related with the ambient manifold. So the ambient manifold itself is M bar, the tangent space, the metric, the Levi-Civita connection, and the curvature tensors. On the other hand, everything which is related to a submanifold will be denoted without the bar. Okay, so we've got the dimensional manifold M, its tangent space, the metric, the Levi-Civita connection, and the curvature tensors. If we consider an isometric immersion of our submanifold in the ambient manifold, then the induced tangent bundle is orthogonally decomposed in the tangent and normal components, as well as the Levi-Civita connection that is also decomposed in the Levi-Civita connection of the submanifold and the normal connection. Sigma will denote the second fundamental form, and A will denote the Van-Ganten endomorphism associated to a normal section psi. Okay, so what is a variation of an immersion? So a variation is just a smooth map F defined in a small interval around 0 times the manifold M, such that at the initial value we've got at 0 we've got the initial immersion, and for every t we've got an immersion. The vector field, defining as the partial of the variation with respect to the time, is called the variational vector field of the variation. So we will say that the variation has compact support if the variational vector field has compact support. Okay, conversely, given a section of the induced bundle by the immersion with compact support, it is possible to define variation f such that its variation vector field is precisely x. And the definition is as follows. So for every point outside the compact support of the x, f is just the initial immersion. And for every point in the compact support, we just move the original immersion using the exponential map, what the vector field x tells us. So now we can define the volume functional associated to a variation that is a functional depending on t, and is just the volume over a relative compact domain containing the support of the variation of the new immersion phi t. Okay, so it is possible to write down that functional in terms of the integral over omega over the square root of the determinant of the metric. And what I like to highlight is that the volume functional does depend both on the on the variation f, and also on the relative compact omega where we consider the variation. Okay, so actually V just measures the volume variation in omega. So to be more clear, let's look at the following picture. So M is the black surface, so we consider a relatively compact domain omega, and inside omega we make a variation of M, which is drawn in red. So what the volume functional measures is just how the volume varies inside omega. However, if we compute the first derivative of the variation, then we'll see that this derivative does not depend on the omega. Okay, so here it appears the mean curvature, which is just the trace of the mean of the second fundamental form, and as I have said, this derivative does not depend on omega, and only depends actually on the variational vector field x, more precisely only in its normal components, since we are integrating the scalar product of x with the mean curvature, which is a normal vector field. So now, a minimal immersion, so an immersion is called minimal if it's a critical point of the volume function for every complex support variation. If we take a look at the first derivative of the volume functional, we immediately see that critical points are actually those with vanishing second mean curvature. Okay, so actually minimal immersion are those with zero mean curvature at every point. Okay, for those who want to dive in the theory of a minimal submanifold, I just present here with 3 texts that I suggest for reading. So the first one is a classic book by Osserman in the 80s called A Survey of Minimal Surfaces, and the first part is a very good introduction to minimal surfaces theory. In the section 3, the author shows what I have just said, that the surface minimized area, or more generally is a first variation, a critical point of the first variation, we think it is a minimal surface. The second one, at the end of the 90s, complete minimal surfacing R3, focus on minimal surfaces in the Euclidean 3 space, and some topics about the theory of complete minimal surface are covered. The last one, it's a recent text from Joaquin Perez, A New Golden Age of Minimal Surface, where the author gives a brief tour of some of recent developments in the classical minimal surface theory. Okay, so now we would like to study how the second variation of the volume behaves. So we start with a minimal immersion, F a compactly support variation, and psi the normal component of the variation vector field x. Then the second derivative of the variation f is given by that integral, and we will see here that this is the scalar product of some functional of the normal section by the section itself. So now it's appeared in this functional the normal Laplacian, some terms involving the second fundamental form, and some terms involving the normal component of the curvature of the ambient manifold in the direction of the normal section side. Okay, so the operator that appears inside the second variation of the volume is what it is called the Jacobi operator, and we will going to denote it L, calligraphic L, and it is a second order elliptic operator over normal section of the induced bundle. Then the index form is just a quadratic form defined using this Jacobi operator. So we have already seen that for a given compactly support variation, the second variation of the volume is just the index form over the normal component of the variational vector field. Hence, the notion of stability appears. So we will call a minimal immersion stable if the second variation of the volume is not negative for every complex support variation. That is, the index form Q is non-negative for any normal section with compact support over M. And we will say that the immersion is strictly stable if the index form is strictly positive for any non-null normal section with compact support. Okay, so our main focus of this lecture is to study stable, or try to study stable compact minimal surfaces. And So for now on, we will assume that our manifold is compact. So we do not have to worry about variation with compact support, because all of them will satisfy that assumption. So we are going to rewrite the stability in terms of the Jacobi operator. In this case, since our manifold is compact, then the Jacobi operator is well behaved, and it's actually behaved as a Schrödinger operator, in the sense that it has a well-defined eigenvalues, set of eigenvalues. The set of eigenvalues is increasing and diverge to plus infinity, and the eigensections forms a Hilbert basis of the space. And we also have a characterization of the eigenvalues as a Rayleigh quotient. So it actually behaves like a Schrödinger operator. So we can now rewrite the notion of stability and introduce also the concepts of index and nullity in terms of the signs of the eigenvalues of the Jacobi operator L. So again, let phi be a minimal immersion of a compact manifold. The index of the immersion is going to be an integer number k, which is exactly the number of eigenvalues of the Jacobi operator that are strictly negative. Okay, it is actually the index of the quadratic form Q. And the nullity is just a dimension of the eigenspace associated with 0. I mean, it is the multiplicity of 0 as an eigenvalue. And again, it is the nullity of the quadratic form Q. And then under the compactness assumption, both numbers are finite integer numbers. Okay? Geometrically, the index is the number of independent direction in which we can deform the submanifolds decreasing the volume. Okay, in the two-sided hypersurface case that will appear in the next part of the talk, it's interesting because if our manifold is actually hypersurface, which is two-sided, that is the normal bundle is trivial, that is we can find a global smooth unit normal vector field to M, then this notion is equivalent to be orientable if the ambient manifold is orientable, but it is not the case if the ambient manifold is not orientable. Then, thanks to this existence of this normal vector field, we can actually find an isomorphism between normal vector field psi and functions over the manifold, which is considered just the scalar product with the normal n. Moreover, since we are in codimension 1 and the normal derivative of n is 0, then for any function over the manifold, the Jacobi operator over the section Fn is actually a Schrödinger operator over the function f times the normal section. This Schrödinger operator, which is called L, distinguished between calligraphic L that we use for a Jacobi operator, is actually equivalent to the Jacobi operator of the immersion. So we can actually study stability for two-sided hypersurfaces, studying just the eigenvalues of a Jacobi operator, of a Schrödinger operator defined on the manifold, whose potential depends on the north on the second fundamental form and the Ricci of the ambient manifold or in the direction of the normal vector field. Okay, so this is the end part this is the final of the end of the part 1 of the talk. In the next talk, I will present some classical examples of stable and unstable minimal surfaces, mainly in spheres. Okay, thank you.